Okay.
Isn't the whole alphabet?
It's a specific number. All right. It's not a variable like X is a variable that can be any number. E is a specific value, like pi. Right. You think pi? You think 3 point. Right? No. It's irrational. You remember what irrational means?
Put in lowercase, exact.
Non-repeating, non-terminating decimal, right? So this is just a Greek letter versus an English letter. Do you remember how pi was discovered, developed?
No. Someone named Pi, probably.
So if you measure the circumference of a circle and compare it to the diameter, you get the ratio pi. That's where pi comes from. It's the ratio of the circumference to the diameter of a circle, right? The number E is that right there. Ish. It's an irrational number as well.
Are we going to have to, what is that called?
E.
Is the literally just called E?
Yeah. So if I say the number E, then you know what I'm talking about.
That's 2.71828.
2.71828 dot dot dot.
Thank you.
It is an irrational number just like pi.
So why is it not fully equal to that? Like pi, you have it set equal to that. And that is
Well, okay, here's a little nuance in math. See, I put the dot dot dot. I should put an equals because that means it needs continues forever. Again, representing the whole number. Whereas if I did this, now it's an approximate, correct? It's a truncation of that number. So that's a little nuance in mathematics that you.
So how is this one?
Okay. How is E developed?
What is
Okay.
that? Another version.
E was developed with this formula. Yes, I know it's weird. It came from the study of what's called sequences and series in calculus. But then backtrack, it becomes a really big application in science. Okay. This number is very important for some reason.
Is that H or
It's a constant that's used in nature a lot. Okay. So this, if n is 1, you have a calculator?
No.
Here's what we're going to do. Go get a calculator. I'm going to show you something.
I'm gonna find one that doesn't break. The tattoo
I'm going to show you using tables. Very handy, very handy. Okay, so put this in your Leica screen with X in it. Okay, so 1 plus 1 divided by X to the power of X. Y equals.
To the power of what?
So yeah, just put X's in for the
Oh, to the
X.
power of X.
We just put alphabet.
So those are the same thing. When you see, the only thing you need to think about is when you see an N, those are integers only, so whole numbers, right? It's just a little thing we do in math, is use N as an integer. X is a real number, it can be anything. Okay. All right, so let's let the calculator do the work here. We're going to go to table set, so second window. We'll start at 1, and we'll change by 1. So it'll be 1, 2, 3, 4. It'll add 1 every time. That's what the change in table is. Okay. Yeah, delta table. And then you can go to your second graph, and it generates the values for you. Yay!
Moving slowly.
So see how
So
it's...
you put it away because this is where the
Anybody lost? Did we set our table correct?
Yes.
Yes.
Okay, and then go to second graph, that's where your table is. So now look at the x values. Look at the y values. What are they getting closer to?
4.
Can we write those steps?
2.7. 7.
You just keep going. What's it getting closer to? 2.7.
4 is 2.6.
And if you just keep going,
Why is mine 2.6?
it's going to pass 2.7, and it's eventually, this is what, the E is the upper bound. It is never going to be higher than that value.
79. I'm almost there. Hold on.
Okay?
Mine's still going, yeah.
Yeah, it's still going to go, but it's never going to be higher than the value of E.
Oh, okay, that makes sense.
Okay? That's where E comes from. It's the
So it'll just
is the upper bound of this when you just keep putting in values. So if you want to test that, go back to table set and start at 10,000 and move by thousands.
How do you go back?
Oh my God, that's going to take forever to go back.
Right? The calculator can't show it, but you see E. And then if it could show a lot of decimals, you would see this continue to go up, but it would never be higher than the value of E. Pretty weird, huh?
Hey, why is that?
Why does it happen?
What is the purpose of the What are we going to use it for?
You'll see. You will. I'm going to show you a little
Does
bit
it
today.
just cut off at that number at E? No.
No, so if you are looking at a graph of this, here's E, right? This function does this. So E is the horizontal asymptote. That would be what the word that you know, right? E is a horizontal asymptote. Okay, so it gets closer and closer and closer to E, but it never crosses it.
Why when you go negative, like negative to negative, it has 4? Like, yeah, I mean, it's in the X. Like if you go,
You went to, so you went negative?
Yeah. What is it?
Well, that's if you plug a negative in here. What does a negative exponent do? Puts it underneath 1, right?
Yeah.
We learned that last week.
Oh, yeah.
So it's going to be 1 over whatever this quantity gives you. So that's what these are. Okay, so that's where E comes from. Kind of something you've never seen before. In calculus, we would call this an upper bound as well. Okay, don't have to remember that, but it's bounded on the top, never going to cross it. Okay, so why is E useful?
Yeah, what if we use it in? I've never seen
I don't
one
know.
halfway sitting down.
Want to trust it, push it. Okay. Thanks, AJ. Okay. Okay, one graph that you will use a lot, e to the x. It's an exponential just like the rest of them.
Oh, you missed it.
Okay, so you know that graph. You know exponential graphs right there.
Yeah.
Okay. We talked about, so on Friday, did the video have exponential growth or decay formulas? Compound interest equations or anything of that nature?
No.
Okay. This is one way to represent exponential growth or decay. Is that Friday? You should have seen something very similar. I think it was that. Did you see that Friday in the video? If you watched it. Oh, it's not, there's no K.
Yeah, that's why I didn't see it.
Okay, these are sister formulas. One has no E and the other has E in it. Okay, we use this one because it's a little more simple usually. But this is your start value. This is your rate. I think when I was here Thursday, we talked about how did we format it? I know it wasn't that. I think I'd remember. Yeah, there are lots of ways to do it. There's lots of ways to write this. I've written it about 5 different ways the last couple of days. So start value, rate, and then your exponential, right? This is the same formula. This is just more of an application-based formula. Okay. So something like, oh, you guys, you probably don't know the history behind this, but do you guys know what DDT is?
What?
No, okay.
Did you align that?
Yeah, DDT was an insecticide that was used on agricultural crops back in prior to the 80s.
Oh, I know what you're talking about.
Okay.
I think it was a
So it kills bugs, right? It kills bad bugs. And it's really good at it. The problem is, it has been determined that DDT is a cancer-causing agent. So when you use it on these fields, it didn't wash off your food, then you ate it, it could give you cancer. So it was banned,
Yeah, everything will be good.
okay? And it doesn't decay very quickly. Right? It's sprayed on, it stays there. It doesn't have a decay that's very quick. So let's say there are 1 times 10 to the 9th kilograms of DDT in the environment in 1973. Okay. That's a lot. Okay, here's the decay factor. See how small of a number that is? So it's not going to decay very quickly.
Smaller than
So write an exponential to represent this. Right, so the amount of DDT in the environment is the initial amount, right? Because our formula is okay. So the initial amount. Okay.
Thought there wasn't PM.
And K is negative 0.0211. So there's an exponential that represents this situation. Okay? And just note that t equals 0 is 1973. We don't have to worry about putting 1973 in there then. You okay on that?
Yeah.
Then you can start to ask questions of like, how much DDT is there in 1985? Let's go with part of it.
Bless you.
And how would I figure that out?
Just plug it in.
Plug one in.
Do the K,
Yeah, would you plug it in for T?
What time is that?
That would be
73 0, so 85 would be 12. So plug that in your calculator. 10 to the 9th e to the power of. So here's how you do that. 10 to the 9th. Oh, quit.
9.
You know where e is?
Yes,
Right there. Second ln. And you're going to learn what ln means this next couple weeks too. There's e and then you negative 0.0211 times 12. Did I type it right?
well, that's not.
So that's how many kilograms of DDT are left in the environment in 1985. So it's 776,312 and what was the last? As opposed to 10 to the 9th, what's 10 to the 9th?
I did not get that number.
Nope, I need to add one extra zero in there, don't I? So you see how much it's reduced? It's about cut by 25%. Yeah, you're typing it wrong. Syntax, see? You know what syntax is?
You're
Structure.
wrong.
The syntax of a language is structure. Semantics is meaning. You put a minus sign. Okay, so there's a science application. You can use this in carbon dating, you can use it in population growth, you can use it in all those applications we talked about with exponentials. It makes things a little bit more simple. Right? Finance is another, finance. Okay, so Yeah. What would you rather have? A savings account? Let's say we have a savings account with $1,000 and 5% interest per year.
Yeah, you do.
Some of you seniors got a little bit of this talk yesterday. Let's put some math to it. Okay, would you rather have that compounded? Do you know what compounding means? It means it's when the interest accrues. Monthly
Or daily.
or continuously? Okay, so this says at the end of the month, they'll multiply by 1.05, that's your new balance. Okay. This one says there's a continuous aspect to the compounding of that interest. Okay. This is going to end up with a better, the more often you compound your interest, the more money you're going to make. Okay. Now, if you have a loan, which would you rather have? Monthly, because it's going to accrue less interest over time, right? You're paying back less money. So loans, longer periods are better. Savings accounts, shorter periods are better. So the continuously compounded uses E as its base. Okay, this is principal, initial principal. Okay, and then you have your rate and your time, just like the other formula, it's just a finance application. Versus this one. For monthly. N is the number of times per year we compound. Does that formula look familiar, by the way?
Yes, that perfectly.
Yeah, it looks like the E formula we have. Yeah. Okay. So it's going to get closer to E the more times we do N. All right, so let's calculate the difference here. The principal is 1,000. The rate is 0.05, and number of times a year is 12, right? How many years? How many years do you want to do? 4 years?
27. Student loans.
What's that decimal? Is it 0.5?
0.05 for 5%. Okay. So calculate that with your devices. We'll see how much you have after 4 years saving. One of the keys to savings account is not to remove the money.
Yeah.
It's just to keep putting it in. That's why it's a savings account, not a spending account.
I feel like you're already assuming what that is.
I'm not assuming, I'm just giving advice.
Right, well, you make like 50.
So 1,000,
1,050.
I got 1,000.
what? 1,050 per point.
1.9. So 91 cents.
All right. Now do the same thing with E and continuously compounded interest. It's a lot easier calculation, first of all. How much? Okay.
1,055.
Is that
What, 48?
times 4?
Yeah. A little bit of difference, right? And that's all it's going to be. It's not going to be very much difference, but you could do the same thing for a 30-year savings plan, and it will probably be a much bigger difference. And you're continuing to add money Okay, so this is just assuming you left $1,000 in the account, didn't touch it. But if you have $1,000 and you add $100 a month, and it's compounding, that's when it gets, we make a mistake.
You put it in the equation completely correct, but he's going up to 1,200.
Which one?
Yeah, I got
Yeah,
1,200.
For the
Yeah.
I got 1221.
1,000, whoop, let's turn it on.
I got 1221.
I'm in rate.
E, .05 times, that doesn't matter.
Yeah, that's what I got.
I got 12.
Oh, yeah.
Point what?
0.402758.
Okay, I'm glad we can go to the 10,000th place in money. I'm gonna assume this is wrong as well, so let's type that in. And check it. 1,000 more plus 14 times
Oh, yeah.
1220.
That's different.
I had put in 12.4,
Yeah,
and that's why it was wrong.
Okay, that looks a lot better actually. But what is there, $1.50 difference?
In 4 years?
Not a big difference, but again, when you get into the later years of like $40,000, $50,000, $60,000 in that account, it's not gonna be $1 difference, it's gonna be like $100 difference, and it's gonna continue to compound. All right, so that's E. Again, pi and E are the two most important numbers in math. Okay? So when you see E, don't think of it as an English variable letter. It is a number, just like pi. Got it?
Yes, sir. Absolutely.
That's good. Okay, 1 through 7, and then I'm going to have you pick one from 8 through 16. There's a variety of applications. Pick one that you might say, I'm going to be in finance, so pick the finance. Or I want to be an engineer, pick something close to engineering. Okay. If you want to be a bum, pick one anyways.
Be a bum.
From 8 to 60.
Yeah, so in 8 through 16, pick a problem, just one. And then here's the rest, so there you go. But, all right.
No, it's not what it was.